that's how it goes. You never ever know about the NWO. Deep behind enemy lines for October 21st, 2020. Breaking news here. Geologists resurrect missing ancient tectonic plate beneath Canada. More earth changes and geopolitical upheaval. And another update to the New World Order from the No Link News Desk. Move over, harp-tards. You'll not see this earthquake news or earthquake prediction from Doomsday Dutchie's magic 3D earthquake crystal ball first. So in case you miss it, or you want to wait around for sloppy seconds from dumb-ass Doomsday Disinfo Dutchie, let's get to the science of things today. Yeah, back in 1998, I was listening to the radio show Coast to Coast AM with Art Bell and heard Mitch Petros rock and shock the global warming Agenda 21 community with his space weather forecast equation. But let me say this again, dumbass Disinfo Dutchie. Mitch Petros came out with this equation in 1998. Not you, okay? This earthquake forecasting equation, Dutchie, he came out with this, not you. So you and your ego and all this intellectual property right bullshit, you copyrights on your channel, well, hey, let's just say you're plagiarizing and ripping off Mitch Petros' work and research, trying to claim you're the super earthquake forecasting guy. Superstar, yeah. You're an earthquake forecasting superstar now because you ripped off Mitch Petros' space weather earthquake forecast equation. Okay. But anyhow, I seen you were saying and showing how the plate tectonics. Let's go to this article right now and bring you up to speed today to kind of like show into the mix how, well, Dutchie just don't have it quite knowledge yet. He likes to cherry pick the data and obviously misleads everyone because, he just likes to generalize using a big giant like rope, like what a cowboy uses to try to get a rope around the neck and bring in a big cow. But the bigger the rope hole you make, well, that's how Dutchie thinks of forecasting earthquakes. I think, he thinks that the bigger the rope is, the bigger the hole, the more earthquake forecast he can predict accurately, right? Yeah, that's how earthquake fishing works here at No Link News. I think it's called earthquake fishing, not earthquake forecasting, Dutchie. I think you're out there fishing for earthquakes, thinking that you can become some freaking superstar forecasting and predicting them. But obviously, you missed the 7.5 earthquake forecast prediction or the precise location. But who am I to point that dumbass shit out to dumbass Dutchie? Yeah. Lost and found. Yeah. Geologists resurrect a missing tectonic plate. Quite interesting enough, I think Disinfo dumbass Doomsday Dutchie brought attention to this plate the other day. Johnny Wu, assistant professor of geology at the University of Houston Department of Earth and Atmospheric Sciences, and Spencer Fuston, a third-year geology doctor student, applied a technique developed by the University of Houston Center for Tectonics and Topography called slab unfolding. I don't think Dutchie knows what slab unfolding means, but, well, we're going to bring him up to speed. Hopefully he can educate all his subscribers to the fact that tectonic plates in the Pacific Ocean, what they looked like during the early Cenozoic era. So do I still have that map? Let me see if I have that over here. Or did I close that out yesterday? No, I didn't. Here it is. Let's load this up. This is what Earth looked like. Maybe I can get it 750 million years ago. So what geologists are trying to resurrect is, well, you know, dumbass Doomsday Dutchie likes talking about the North American Craton plate. I think he likes to give a lot of credit to that. Well, now we're going to find that these ancient plates, the existence of these ancient tectonic plate, scientists called resurrection, as long has been a topic of debate among geologists, with some arguing some of these plates are never real, Dutchie. So we want to go to the Cenozoic era. Okay, this 3D ancient Earth globe, this is what Earth looked like 750 million years ago. So how many million years ago was this age? 40 to 60 million years ago. Okay, so we're going to move up from 750 to 40. Let's go here to 50 million years, see what Earth looked like 50 million years ago, Dutchie, on this magic 3D earthquake crystal ball. So back into and bringing you up to speed, some have argued that the plate resurrection has long been a topic of debate, but some arguing it never was real. Others say it's subducted, moving sideways and downward and into the Earth's mantle somewhere in the Pacific margin between 40 and 60 million years ago. Okay, the globe you see there is approximately what Earth looked like 50 million years ago, Dutchie. A team of geologists at the University of Houston College of Natural Sciences and Mathematics believes they have found the lost plate in a northern Canada by using existing mantle topography images. Similar to a CAT scan of the Earth's interior, the findings published by the Geological Society of American Bulletin could help geologists better predict volcanic hazards as well as mineral and hydrocarbon deposits, Dutchie. Yeah, many of those out there in the know realize, hey, at one time, you know, all those fossil fuels were once living creatures on Earth's surface before they, mysteriously were sucked underground and turned into hydrocarbon deposits, you know. You know where that oil comes from, Dutchie? Yeah, he probably doesn't have a clue, does he? But hey, I just want to point out today's flavor of the day. Michigan flavor of the day is Purple Haze. Shout out to Spider-Man, just to give you a heads up today. If you haven't seen the news, never know. The State Line has a sale today. That's today's top sale at Remedy. Remedy State Line, buy one, get one, 31% off. All your smoking needs. Puffing needs, yeah. So, once again, flavor of the day, Michigan flavor of the day, Purple Haze. So, volcanoes, here they say, volcanoes form at plate boundaries. And the more plates you have, the more volcanoes you have, said Johnny Wu, assistant professor of geology in the Department of Earth and Atmospheric Sciences. I wonder if Dutchie knew that. Volcanoes also affect climate change. So when you're trying to model all this global warming shit, these people that try to, blame humans for causing all this hurt, changes, volcanoes also affect global warming. So what are they going to try, looking at this scientific data and understand how climate change has happened since before humans? You really want to know what the Earth looked like, way back in the day before man was even on it? But hey, who am I to point out, today's top news? Oh, yeah. CO2 gases. Yeah. caused climate change before humans were on the planet. But who am I to point this out? Yeah, global warming wiped out and caused extinction. Yeah, and it wasn't humans' fault. So this all plays right back in and affirms Mitch Petros' science of cycles equation. Whoops, that's not what I want. Mitch Petros' science of cycles equation, and affirms how the Earth and the Pangea and cosmic evolution has changed the shape of this planet and its land masses. Johnny Wu, assistant professor of geology at the Department of Earth and Atmospheric Sciences, says volcanoes also affect climate change. So when you are trying to model the Earth to understand how climate has changed since time, you really want to know how many volcanoes there have been on Earth. Well, we know Dutchie is finding a lot of them dormant volcanoes out there in the desert, west desert, southwest United States. Yeah, California, Nevada, Arizona, Utah, Nevada, Wyoming, Montana. Yeah. But, hey, who am I to point out that the topography of these plates unfolding seem to be, hey, let's go back to the early Cenozoic era, where the rigid outermost shell of Earth, or lithosphere, is broken into tectonic plates. And geologists have known there were two plates in the Pacific Ocean at the time called Kula and Farallon. But there has also been discussion about the potential third plate, resurrection, having formed a special type of volcanic belt along Alaska and Washington State. Isn't that interesting? Well, let's see. Let's see if I can get to give you some diagrams. Obviously, this 3D magic earthquake crystal ball isn't going to cut it for most of you out there. No. So we're going to have to rely and moving to a new scene to show you what I mean. Give me a second here. Yeah, there's the article we're talking about here. So this pretty much destroys Doomsday Disinfo Dumbass Dutchie's latest video this week on the plate topic that he was talking about. Yeah. On the Cascadia subduction zone. Yeah. So here's a topography of that lost plate where more volcanoes can be seen, Dutchie. So 60 million years ago. Okay, now we got this over here. Yeah, this one here. This will show, illustrate how these plates are colliding on the west coast, Dutchie. Yep. Which just throws your whole flipping seismic pressure earthquake transfer theory upside down, doesn't it? So as the ocean spreads and forms new landmass underwater, pushing these plates up against the west coast of the United States, you have these two plates here, Dutchie, out here in the Pacific Ocean. See that? Oh, man. And he wants to try to bullshit people on the fact that he knows all about tectonics. But he's missing the missing slab. He's missing the missing data here, isn't he? Once again, like I said, he likes to cherry pick shit off of scientists and claim intellectual property rights off of stealing somebody else's research. You know, he's famous for that shit. But anyhow, we know that the plate that is moving is being pushed by other plates and reshaping the Earth. Part of the Earth changes and science of cycles here at No Link News. We'll move and bring you up to speed and let you hear what Johnny Wu, an assistant professor at the University of Houston, and Spencer Fuston, he'll bring it all up to speed to reconstruct how these tectonic plates in the ocean, what they looked like in the Cenozoic era before they started moving and creating the Cascadia subduction zone. Dutchy. Yeah. So a 3D block diagram across North America showing a mantle topography reveals the slab unfolding method used to flatten the Farallon tectonic plate. By doing this, Fuston and Wu were able to locate the lost resurrected plate. Let's give credit to the University of Houston Department of Earth and Atmospheric Sciences and College of Natural Sciences and Mathematics to help reshape and understand the unfolding technique to the mantle and subducted plates stretching under Canada.
I'm Spencer Fuston, a PhD student here at the University of Houston, working with Dr. Johnny Wu. I just wanted to start by saying thank you to Dr. Collette and the group as a whole for giving us this opportunity to not only present some of our work, but also arrange some of the previous talks. Very much enjoyed those and been learning a lot about Canadian tectonics as well as tectonics elsewhere. So what I wanted to talk a little bit about today was some of our work related to structurally unfolding and restoring subducted slabs in the lower mantle below Western North America, with particular implications for the presence of the resurrection plate. But before I get into that, I wanted to start by highlighting the diversity of published plate tectonic scenarios in this part of the world since early Cenozoic time. So the most simple tectonic models of this part of the world involve the subduction of a single mid-ocean ridge residing anywhere from northern Mexico to the Pacific Northwest, all the way over to western Alaska. And the position of these, where this mid-ocean ridge is subducted, primarily been motivated by suites of near-trench magmatism present in both Alaska, which motivates the Alaskan scenario, and the Pacific Northwest, which motivates kind of the Pacific Northwest example. However, the challenge that these models have to deal with is that each scenario, whether it's the Alaskan scenario or the Pacific Northwest one, can only account for one of these coeval suites of near-trench magmatism at a time. And to try and address some of these difficulties, there's an additional class of plate tectonic model which tries to explain both suites of near-trench magmatism at the same time. What we're calling, or what's been called the resurrection plate model, does so by having, instead of a single mid-ocean ridge subducted below Western North America, now there are two mid-ocean ridges, one subducting below Alaska and the other subducting below the Pacific Northwest. And those two mid-ocean ridges bound an additional tectonic plate known as the resurrection plate. An alternate possibility for how to explain these two suites of near-trench magmatism, or what we're calling the mobilist model, where there's still a single mid-ocean ridge subducting below somewhere around the Pacific Northwest. But in this scenario, the near-trench magmatism in Alaska is explained by translating the Chugach terrain which is what those intrusions are emplaced into, and moving that down to intercept this mid-ocean ridge. And then as the Chugach terrain migrates to the north over time, the progressive suite of near-trench intrusions are emplaced. A very recent suggestion is that during this time period, Western North America was a transform boundary. So really the goal of my talk today is to try and narrow down which of these this wide variety of possibilities are the most consistent with the record of subduction we have from mantle tomography. And the approach that we're going to use to do that is, rather than relying on upper plate geology, we're going to try and reconstruct the subducted lower plate and build a plate tectonic model based on that lower plate reconstruction. So the way that we do that is we use many different mantle tomographies of the upper mantle below Western North America, and we map these slabs, which are still connected to subduction zones below Alaska and the Western US. So we map those slabs in 3 dimensions and then structurally unfold them back up to Earth's surface before inputting those reconstructions into a plate tectonic model. And because our inputs to those plate tectonic models are from mantle tomography, they're actually independent of all of the upper plate surface geology constraints. So as a result of that, we can actually compare and test our tomography-derived plate tectonic models against the upper plate geology and validate them that way. So jumping ahead here, what our results suggest is that a model which includes a resurrection plate is actually the model that's most consistent with the record of subduction that's present in the mantle imaged via mantle tomography. So I've been talking a lot about near trench magmatism in Western North America. So I thought I should highlight exactly what I'm talking about here. So there are 2 broad suites of near trench magmatism in the Pacific, or in Western North America. One very famous example in southern Alaska here, where what's called the Sanek-Baranoff suite of near trench intrusives are emplaced within the Chugach terrain. On the right here, we have distance along the margin plotted against time, where 0 represents a little west of Sanek Island, and 6,000 here is in Southern California here. So what we can see is that this broad group of near trench magmatism represents that Sanek-Baranoff suite of intrusives. And we can see as they broadly young from west to east and from north to south, and make a very distinctive trend here. And then partially overlapping in the same time period in the Pacific Northwest, there's kind of a comparable suite of near trench magmatism present in Northern Oregon, Washington State, and then in on Vancouver Island, and even more north in British Columbia. So one thing to note is that these 2 broad suites of near trench magmatism merge somewhere in between 40 to 35 MA, become a single suite of near trench magmatism. So this magmatic record is going to be the main data set that we're going to compare our slab unfolding results against as we go forward. And that's just simply because it seems that near trench magmatism is kind of the most direct record of mid-ocean ridge subduction that we can get at. And the reason for that is that as mid-ocean ridges are subducted, the kind of 2 opposing plates, as they subduct, tend to diverge within the mantle, opening up what's called a slab window, or essentially just a gap between the two descending slabs. And this allows a stenosphere below the subducting slab to actually upwell through that slab window and mix with the stenosphere above the slab. And this results in elevated, significantly elevated heat flows and partial melting in the forearc regions associated with these subduction zones. One really great modern example of a slab window that we can image with mantle tomography is here in southern Chile, where the Nazca and Antarctic plates are subducting below South America. And the ridge between the two is subducting, and we can image this subducted slab and see the slab window between them. So moving back to Western North America, really the slabs that we are most interested in are not the slabs in the lower mantle. Those are interesting as well, but for this talk, we really want to focus in on just the slabs in the upper mantle, which are still attached to subduction zones. These are the ones that we can interpret with the highest degree of confidence, and we can place them into a tectonic model with the highest degree of confidence. So I'm showing here what we're calling the Cascadia slab below the Western US, but also we also looked at we're calling the Alaska slab below Alaska. So if we zoom in on this upper mantle Cascadia slab, we can start to quantify the amount of subducted oceanic lithosphere that's held within the slab anomaly by defining what we're calling the slowest closed contour. And that is the slowest contour which closes around a given slab anomaly. So in this case, it is the 0.1% DVP contour. Essentially we need to do this to define the edge of these subducted slab anomalies. And once we define that edge, we can really start to quantify the amount of oceanic lithosphere that's held within this anomaly by measuring a cross-sectional area for this given slab and structurally unfolding that and restoring it back to Earth's surface. We restore it back to Earth's surface by assuming an initial thickness of oceanic lithosphere. The thickness we've assumed for this study is 80 kilometers thickness. And so this unfolding process is partially just that balancing of the cross-sectional area versus the length, or the assumed thickness, and getting a length, and partially from a density depth correction that we apply to these cross-sectional area, the cross-sectional area by depth slice. And this is just to account for increased density with the mantle, which are going to compress the slab and make it look smaller than it is. So we put that all together and get a calculated length of oceanic lithosphere that's held within a given anomaly at a given transect. So I'm showing an example of this methodology for one transect, but then we can repeat this process for many transects along strike, up and down the margin. An example of what that would look like is that each of these dark lines here that I'm outlining with the mouse would represent one unfolded slab length from one transect. So, and then we would repeat that for each of these dark lines, and where each of those lines represents one slab unfolding measurement. And then we can take these measurements and input them into a kinematic plate model and develop a tectonic model around them. But I got a little bit ahead of myself. Before we can unfold these slabs, we first have to know where they are and what these slab geometries look like. So to do that, we developed and mapped these slabs in 3 dimensions with what we're calling a mid-slab surface. And that's just the geometry of the exact middle of the slab throughout. So we're just essentially making essentially a structure map of the geometry of the slab. So here below Alaska at shallow depths, around 300 kilometers, you can see that the Alaska slab broadly has kind of a steeply dipping geometry, kind of excluding this area below mainland Alaska, where we have flat slab subduction. And then at deeper depths, around 150 kilometers, the Alaska slab actually appears to shallow out and rest more or less horizontally on the top of the lowermost, or the uppermost lower mantle. Incorporating many of these mantle tomography models together, we come up with a kind of overall mid-slab surface for the Alaska slabs, it looks like this. So some things to note is that from east to west, the overall aerial extent of the Alaska slab appears to increase. So that is to say that the western part of this slab appears to be more aerially extensive than the eastern part. Another thing to note with the Alaska slab is that I'll talk about this in more detail in a minute, but we've actually also noted an additional slab, which we're calling the Yukon slab below modern day Yukon, which appears to be disconnected from the Alaska slab and turns out to be a fairly critical part of the interpretation of the tectonics of this part of the world. So I'll show that here in a little bit, but for now we'll move further south to the what we're calling the Cascadia slab and repeat kind of a similar process. So at shallow depths, 300 kilometers depth, we have more or less kind of a normally dipping slab, and then at deeper depths, we have actually kind of a similar story where the Cascadia slab appears to shallow out and rest horizontally on the lower mantle. And then in terms of this overall mid-slab surface map, actually I kind of have a similar trend where the northern part of the Cascadia slab seems to have a much smaller aerial extent than the southern part of the slab. So then, as I mentioned a minute ago, there's really not too much in the way of coherent subducted slabs in the upper mantle below Western Canada. We can see here in a kind of a strike section parallel to the margin, which goes through the Alaska slab here, and then the Cascadia slab here. But you can both see both of those slabs you can see fairly well. But then in the intermediate region below Canada, it's much more sparse, and really the only kind of whiff of subducted slab that we get is this Yukon slab here, which is not imaged particularly well in this current tomography, but in a very recent local tomography that I'm showing now, this Yukon slab is much better imaged and appears to be really the only example of subducted slab, which is readily imaged in the upper mantle below Western North America, or Western Canada even more specifically. So one of the main questions we're trying to answer here is, why is there so little slab below Western Canada, and what is the significance of the Yukon slab, right? The only kind of fragment subducted slab that appears to be there. And we'll try and answer that question as I go. So now we can put all of these mid-surface maps together and actually do the unfolding analysis. So we can see here is that on either of these maps, we have transects 1 through 5, then 6 through 10 here. And then on the right, we have two plots. Both are the unfolded slab lengths against latitude for the Cascadia slab, or against longitude for the Alaska slab. And within these plots, transects 1 through 5 are notated here, and then 6 through 9, or 6 through 10 are notated here. What we can see is that we've done the analysis with not just one tomography, but as many tomographies as we could get our hands on, which image these slabs well. So each of these data points, or group of data points, represents a different tomography, and we've kind of brought them all together to kind of outline the range of possibilities you get when you unfold these slabs with different tomographies. And what we've done is taken the mean of this range of values for each transect and built that into our reconstruction. So looking at the unfolding results broadly, what we can see is that the westernmost extreme for the Alaska slab and the southernmost extreme for the Cascadia slab are really the two areas where we can unfold the greatest amount of subducted oceanic lithosphere. And then the intermediate regions, as you go inwards towards British Columbia and either slab, show a trend which is a systematic kind of decrease in the amount of subducted slab that you unfold as you move inwards towards British Columbia. So that's the overall trend that you pick up from doing this slab unfolding result. So we're really interested in moving from just the unfolded slab lengths into actually a kinematic model and inputting these restored lengths of oceanic lithosphere into a kinematic model and seeing what that tells us in terms of the tectonics. And that's what we've done here. So on the upper part of the slide here, as I said before, these dark lines, which are plotted next to each other, represent the lengths, the unfolded slab lengths that I just showed you on the previous slide. And we put them all next to each other, and we can draw a polygon around all of these unfolded slab lengths, which essentially represents the total aerial extent of these subducted oceanic plates that we can reconstruct with mantle tomography. So what we can see is that we can start to compare what these reconstructed oceanic plates, how they compare with the upper plate geology in terms of the near trench magmatism. So we can do that by plotting these points of intersection between our reconstructed Kula plate, for example, and North America. So that gives us 1 point here that we can plot. Again, we're just plotting distance along Western North America against time, where 0 is Sanic Island and 6,000 is Southern California. So this first intersection point plots somewhere here for the Kula plate, and then for the Farallon plate at 60 MA, this intersection point plots somewhere here. So then we can repeat this process for a 50 MA time slice, right? So now these two intersection points of our reconstructed slabs plot here, and repeat that again for 40 MA. Now these two intersection points plot here. So now I'll just finish out plotting all those intersection points, and all those intersection points are actually what bound these colored blue and green areas on the plot down below. And also we've plotted the intersection points of the Yukon slab in purple here. What we can see broadly is that the amount of oceanic lithosphere that we can reconstruct with mantle tomography isn't all-encompassing, right? There are gaps that are left behind after we've reconstructed all of the oceanic lithosphere that we can. And one thing to note is that that unconstrained area that's left over, this white area between our blue, purple, and green areas, actually coincides very nicely with the observed near trench magmatism that is one of these upper plate constraints. So this gives us some indication that perhaps the mechanism that controls the preservation of subducted slabs in the mantle also controls the generation of these near trench intrusions. So this leads us to the interpretation of the gap between our three reconstructed plates representing thermal erosion about 2 mid-ocean ridges, which were subducted below Western North America. And that's what's represented by these black dashed lines here. So we have 2 reconstruction gaps at 60 to around 50 MA, which then merge going forward in time. So what we've done as a straightforward interpretation of our constraints is we've modeled 2 mid-ocean ridges within the exact midpoints of these unconstrained areas, these areas that are left unconstrained by after our slab unfolding constraints are taken into consideration. So then we can take these mid-ocean ridge intersection points where essentially at each time along this plot, this black line represents the position along the margin where that given mid-ocean ridge is intersecting the trench. So we can take these ridge trench intersection points and input them into our plate tectonic model, and by doing so, model the positions of these mid-ocean ridges. And that is what's shown and is what that's what is controlling where we've drawn these mid-ocean ridges on the maps on the upper part of the slide.
Okay, I think I captured all that. And from what I summarize, the DeLuca Fuca plate that Doomsday Dutchie mentioned the other day that was moving seems to be moving because it's being pushed by these resurrected ancient plates that have just been discovered. Yeah. So this breaking news. So you never know. We're going to wrap up this and move on. Got a lot of news today breaking here at No Link News. Just to give you a heads up on this reconstruction and resurrection of these Farallon and Kula plate. Remember now how this all plays a intricate part as the mysterious fifth element dries and binds the universe together. The mysterious fifth element is still... So we've got, the normal four elements of earth, water, fire. The traditional. And the fifth mysterious, what's causing the earth to move and these plates to break apart and the movement like fluidity. So 60 million years ago, from 60 million years, so every 10 million years, it summarizes how the movement of these plates are colliding with the North American plate, triggering volcanoes and earthquakes, Dutchie. Since obviously you're a smart earthquake forecaster superstar. Yeah. No wonder nobody gives you any credit. I mean, even these scientific doctors have debunked your fucking bullshit make-believe fantasy island theory of earthquake seismic pressure transfer bullshit. Yeah. So, see how seismic pressure transfers here, Dutchie? You see how these plates are putting pressure up against these other plates, pushing up against the North American plate, and causing the volcanoes and earthquakes yet, you dumbass? Huh? Or are you still going to be pushing people off into the fucking, off the fucking plank off your ship because they don't want to agree with you, so you call them trolls, huh? Yeah, we know how you play your freaking cherry-picking game, you dumbass. Trying to forecast earthquakes with your little red lines, drawing them up down the plate boundary zones. Like some kind of energy travels along. No, dumbass. You got your head up your ass when it comes to freaking earthquake energy lines going through and down and around and up and in, including this North American craton continent. But hey, keep your fantasy. Keep making people believe your lies, because eventually they're going to wake up and see the truth anyhow. And it's going to be, you're going to be left without any, you're going to be left like, an emperor with no clothes on there, dumbass. You don't have all the knowledge of this earthquake, knowing how and every intricate freaking part, because here, let me just slid over here and tell you know what I'm saying. We're going to go back here in the news and bring you up to speed today in nice just fashion. What do I have in the science continue? Oh my goodness. Here's another discovery, dumbass Dutchie. You're discovering all kinds of stuff. Well, I'm discovering shit over here at No Link News. Your dumbass hasn't even got a clue about. You know what I'm saying? You're discovering freaking hot spots and volcano fucking steam plumes. What a fucking scumbag you are. Because look here. Published October 16th, 2020 at the University of Bristol. A pioneering technique which captures precisely how mountains bend to the will of raindrops. Now, how are you going to help solve this enigma there, dumbass Dutchie, huh? How are you going to solve this dumbass fucking seismic pressure transfer theory bullshit when a new technique here I'm discovering here at No Link News? Precisely, how do you predict earthquakes when raindrops make mountains move? The dramatic effect rainfall has on the evolution of mountainous landscapes. This is something, the water, you don't want to debate about, dumbass Dutchie. You got your head sucked up far up your ass. You don't even know and realize the continents are moving, and it's all because of fluids and water. And new research led by the University of Bristol and published today in Science Advances clearly calculates its impact, furthering how to forecast earthquakes and understand how peaks and valleys have developed over millions of years. This study, which focused on the highest, mightiest mountain ranges, the Himalayas, also paved the way for forecasting the impossible impact of climate change on landscapes and, in turn, human life. So there we go, right back to affirming Mitch Batro's Earth Changes and Science of Cycles research. Yeah. Another shout out. So, lead author Dr. Brian Adams, Royal Society, Dorothy Hodgkin, fellow at the University Cabot Institute for the Environment, said, "It may seem intuitive that more rain can shape mountains by making rivers cut down into rocks faster. So dumbass Dutchie still don't have a clue the other day when the earthquake swarms over there in California underneath a frickin' new dam helps affirm the fact that rain can erode the landscape, and quickly enough it sucks into the rocks and into the earth and effectively pulling mountains up very quickly. So now this theory dumbass Dutchie doesn't even have a clue about. He's forecasting earthquakes and making predictions on shit and banking on his fucking, bankrolling his fucking wealth on all this bullshit. Now has just been fucking totally shattered and destroyed. Just like Mitch Batros destroyed all the freaking global warming and Agenda 21 experts. So now this theory has been debated for decades because the measurements required to prove them were so painstakingly complicated. So that's what this discovery makes such an exciting breakthrough. And as it strongly supports the notion. Hold on a second. It strongly supports the notion. Strongly supports the notion, Dutchie. It strongly supports the notion, Dutchie. I'm back again. Hey. Just to give you a heads up, I'm going to torment you because the study based in the Central and Eastern Himalaya, Bhutan, and Nepal. But while there's no shortage of scientific models aiming to explain how this Earth works, Dutchie, the greater challenge is enough to observe and test to see whether or not I'm accurate or these scientists are accurate. So again, when it comes to forecasting earthquakes, I just want to say that when the cosmic particles collide from outer space with the Earth's magnetic field, it heats up the Earth's core, causing the Earth to expand, and when the Earth cools down, it shrinks. So when a cosmic particle from outer space reaches Earth, it's likely to hit sand grains on hill slopes as they are transported towards rivers. This is back to the mysterious fifth element again. When this happens, some atoms within a grain of sand can transform into a rare element. By counting how many atoms of these elements are present in a bag of sand, we can now calculate how long it will take this sand, therefore, by heat, pressure, and fermenting, and quickly turning it into a diamond. Once again, the capstone on the Masonic pyramid. So here we go, Dutchie. We have rain, water, and erosion rates all over mountain ranges. And have you compared and the steepness of this rainfall and the huge problems because this weight upon the Earth's crust is difficult to produce the data and interpret to realize that this weight may trigger earthquakes on the fault lines yet, dumbass? All right, so here we go. We tested a wide variety of numerical models to produce the observed erosion rate patterns. This model shows us for the first time to qualify how rainfall affects erosion rates in rugged terrain. So researcher collaborator Professor Keelan Whipple, professor of geology at the Arizona State University, said, quote, "Our findings show how critical it is to account for rainfall when assessing patterns of tectonic activity using topography." Well, didn't they just do that with this mysterious resurrected plate? Scientists using topography, Dutchie? Yeah, that's something I don't think your magic earthquake 3D crystal ball is essentially in providing data with. Yeah. So let's address how much the slip rate on tectonic plates may be controlled by climate-driven erosion at the surface. The study findings also carry important implications for land use management, infrastructure maintenance, and hazards in the Himalayas. So once our data has, been addressed, this new frontier of landscape evolution, cosmic rays, cosmic rain, cosmic energy, the Mayan fifth element, they call it, to understand the influence of each other, of all these elements, how they play a key role in likely predicting future volcanic eruptions, dumbass Dutchie. So groundbreaking discovery. I think we ought to title the headline for today's show, "Groundbreaking Discovery," just to irritate dumbass disinfo Dutchie with this. Yeah, instead of breaking news, there we go. Literally, groundbreaking discovery. Yeah, that's today's title of today's show. Let's move on to this latest news now. We know that rainfall can actually move mountains, Dutchie, and trigger earthquakes. Now we have, I want to get this one. No, I don't want to, before I go to that one, let's get this one. Yeah, we talked about this the other day as I, talked about cosmic evolution and how new research explores how superflares affect planets and habitatability. So largest solar flares are examples how to understand how much radiation from superflares can trigger the Earth's core to heat. Among other things, many researchers believe that it can wipe out the electrical grids and do all kinds of other crazy shit to the planet. And, well, I don't think your global warming and Agenda 21 nuts out there, experts have factored in when the next super flare occurs, well, we're going to find the mess we're going to be in, experiencing, super earthquakes too. This is something that Mitch Petros, taught me along the way all these years since 1998, dumbass Dutchie. So let's move in and add into the mix in before I close out today's show. Oh, we're talking about solar flares, weren't we? My goodness, we gotta bring you up to speed today with today's show. Oh yeah, we gotta forget. We can't forget today's show about solar flares. Yeah, well, we got a geomagnetic storm, G1 magnetic storm watch now in effect. Also, the last 24 hours show we had 2 B-class solar flares occur from the sunspot. Let's see what it's space weather call it. It's 57. So, but it's probably dying out. That sunspot was weakening yesterday. It didn't possess as much energy as it did, but 2776 is still hurling, solar bombs. An outburst of electromagnetic activity, and these magnetic explosions are about 1/1,000,000th as powerful as true solar flares. Latest study today. So, yeah. What do solar flares have this all to do with anything? Well, I also just picked up to the breaking news that asteroids also have aurora borealis, the northern lights, in the latest breaking headlines. I want to move and show you that the magnetic fields that Mitch Petros explained during these Earth changes and science of cycles is a theory long discussed by many of us here at No Link News. About the local magnetic spots now suggest the moon is also a result of the universe magnetization process. So yes, the magnetized universe, as massive bodies like the moon and asteroids and other planets all possess the internal core and geodynamo effect, just like on planet Earth, Doomsday Dutchie. They have earthquakes and volcanoes. Presently, today's October 15th news headline in the Science News: simulations show that alternative exploratory models such as asteroid impacts do not generate sufficiently large magnetic fields. Well, presently, the moon does not have an internal magnetic field as observed on Earth. However, there are localized regions on its surface up to several hundred kilometers in size where a very strong magnetic field prevails. This has been shown by measurements on rocks from the Apollo moon mission. Since then, research has puzzled about the origin of these magnetic spots. One theory is that they are in some way remnants of an ancient core magnetic field, possibly similar to what still be observed on Earth today. So this is the little news. Yeah, magnetic fields on the moon. Here's a core consists of molten and solid iron as its rotation generates the Earth's magnetic field. So here's the long-term subject in this new discovery. Why Earth's inner field on the moon, as it rotates, helps, well, let's say the origin assumed to be because the moon, unlike the Earth, has no atmosphere to protect it from meteorites and asteroids. Such massive bodies can hit it with full force and pulverize and ionize materials on its surface. So as a cloud of charged particles, the mysterious main fifth element, also called plasma, created in this way, flows around the moon, compresses the magnetic solar wind present in space, and thus strengthens our magnetic field. At the same time, when solar wind induces a magnetic field in the moon itself. So at the surface opposite the impact, all these fields are amplified to create the observed magnetism in crustal rock. So there was, not only do we have water making mountains move, dumbass doomsday disinfo Dutchie. Now we have magnetized rock. Now examples of the moon, its craters, in regard to the fact that this magnetized rock may attract asteroids to it, resulting, in collisions like you see on the moon, since they have a weaker magnetic field. And 1,000 times more weaker, that means the moon's going to have more asteroids hitting it. Something the mysterious fifth element may be such dark energy yet to be explained by dumbass disinfo Dutchie. How is it? Yeah, I happen to know these things in advance from our Mayan elders. I do. But dumbass Dutchie doesn't have a clue what I'm pointing to. No, he don't. Magnetic fields. And how super flares affect the weakening of those, how they affect the weakening of our magnetic field. And when we have a weaker magnetic field, we're going to get more asteroids and meteors and fireballs. You know what I'm saying there, dumbass Dutchie? Been trying to tell you this shit for how many years now? I don't know. You guys keep ignoring me. But who am I point out one day? Earth's going to lose its magnetic field. The Earth's magnetic field's about ready to flip upside down, and we're going to see these signs in the skies. And I'm just forecasting these ahead of time just to let you know why I keep an eye out for you all ahead of time. Matter of fact, let's go here to finish up today's show. Noticed we had solar winds weakening Earth's magnetic field today. Let's go back here and see the real-time data. Whoops. Let's validate this. This is not what I'm looking for, but this is going to still show, since we're going to a minor geomagnetic storm effects right now. We'll see what the geoelectric field looks like with this up-to-date chart, real-time minute. Give it a second here to load. Not much activity today yet. Let's see what we got for solar winds coming in. Move over. Well, I gotta let these load pages load. Go to GOES. Yeah, like I was pointing out, going back, we had 2 B-class solar flares in the last 24 hours. SpaceWeather.com has issued a G1 geomagnetic storm watch. It looks like over the last couple hours we've had a KP4 index, a KP4 radiation. And let's see what we load, see how the animation of the ionosphere map. Since all you HARP-tards out there still don't have a clue what HARP stood for or what it meant when it was researching the High Aurora Borealis Research Project. But who am I to point out? HARP was studying super solar flare and what its effects would be if one were to hit the planet. But you HARP-tards still got your head stuffed up your ass trying to figure that HARP caused a triggered Earth and HARP is responsible for weather weaponry. Well, this shit, in likelihood not there be, because when a super solar flare hits, there ain't gonna be enough HARP energy to even be able to reduce the impact of this radiation event. But there you go. Looks like right over the Indian Ocean and Western Africa, a lot of magnetic oscillation going on. Yeah. So what does this all mean in the real-time solar wind? Well, let's see what I got. Come on, Slowfo. Well, actually, the wind speeds have diminished. It's not that high right now. The density was up just a few hours ago. So we're not really getting blanketed with a solar wind yet. But as it goes, man, look at that dip in the magnetic field that magnometer shows. Way down low, down in the nanotest, down below 10 almost, yeah. That's going to be a key sign, too, of something brewing in the forecast, Dutchy. Just to let you all know, what is the juggernaut? What does this magnometer show? No data. Oh well. Oh well. Behind. Maybe Dutchy's got a conspiracy why they may be hiding it from you, huh? Yeah. Well. Well, computer just froze up, so I guess that's a good time to say and close out today's latest groundbreaking discoveries. I am Never Know Patriot Broadcasting and Liberty Tree Radio field reporter number 8,510. And as always, God bless the Republic. Death to the New World Order. We are on the march. The empire is on the run. The empire is on the run. We shall prevail.